Alright, in this video we are going to talk about a reaction that has kind of an odd name, the Malonic Ester synthesis. Now, it's kind of a misleading name because it implies you're making an ester, but the ester is actually this guy here. This is actually used in the synthesis of something else. Alright? This is still to do with acidic hydrogens like you've been seeing in previous videos in this chapter. And basically what this allows you to do is it allows you to take an alkyl halide. Let's say we have 1 bromopropane here. And from that we want to make a carboxylic acid that looks like this. Let's say we want to make this. Now, adding carbons, we've seen before that we would use a Grignard reaction for this, but adding 2 carbons, where one of the carbons as is a CH2, well, that gets a little bit more complicated. And that would involve several steps to actually get from here to here. What this malonic ester synthesis allows you to do is to take an alkyl halide and make a carboxylic acid from it, but add 2 carbon atoms in the process. So for that reaction, for that reason, it's actually really kind of a useful reaction. Anytime you can add carbons, in this case you would have added this carbon and this carbon to this alkyl halide. Anytime you can do a reaction to add carbons, that makes that sort of reaction potentially useful. However, and this is the one thing that is potentially confusing about this, is the reaction always starts with the same species. Alright? The reason why this is called the malonic ester synthesis is because every time you do this, you always start with this molecule. This is known as malonic ester. If you were to try and name it using our IUPAC rules, well, the first thing is you can see it's an ester. In fact, there are 2 ester groups, so it's a diester, so we're going to need the name di-O8. Let me just get rid of this. So you can see we're going to need di-O8. Alright, our parent chain is 1, 2, 3 carbons, so propane, and we have 2 ethyl groups, so therefore diethyl propane di-O8. Now, this is also known as malonic ester. Malonic ester is the common name. It's the name it used to be used. It's the name that doesn't make any sense in terms of the actual structure, but it's the name that stuck. Frankly, malonic ester is easier to say than diethyl propane di-O8, but that latter name actually makes more sense. What I want to spend a little bit of time on is how can we use this and what does the mechanism actually really look like. Alright? Now, if you looked at previous videos in this chapter, you will notice that we've been talking about the concept of the alpha hydrogen. The hydrogen on a carbon next to a carbonyl group. This is an alpha hydrogen. Alright? As is this. And we saw that because of the pi bond here and resonance, when you remove this hydrogen, this is more stable than you would normally expect, until this and this are more acidic. And also in one of my previous videos, we had talked about what happens to the acidity of a hydrogen if it's between 2 carbonyl groups, and we said that acidity goes way up. So in other words, if I do something like this, if I was to draw out a molecule like this, in fact, let me go ahead and draw out, why don't I draw out, start again, how about I not screw it up? Let's go back here, okay. Let's actually draw out malonic ester here. So here is one side of our malonic ester. Let me draw this out. La 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 la. Talk amongst yourselves. Wow, the Oscars were great last night, weren't they? Well, if you're into that sort of stuff. Okay. Let's put on one of these acidic hydrogens. In fact, let me just draw both on them. If you were to compare that to this, for example, this is also an ester. And you look at the acidic hydrogens here. I'll just draw one of those. Which acidic hydrogen is more acidic? Is it this one? Or is it one of these? Well, it turns out it's these 2, or one. Or both of them are acidic, actually. Because there's more potential places to put the negative charge and thus more resonance structures here. So what that means is, for which of these two would we need a stronger base to be able to remove that hydrogen? Well, we need a stronger base here, we need a weaker base here. And it turns out that for a molecule like malonic ester here, a base such as ethoxide, O18-, actually works just fine. Okay, now to make matters a little clearer, I'm going to remove this hydrogen because we're not actually using it right now. And we're going to see, essentially, in this whole reaction, what happens. It shows that we have two steps. We first throw in malonic ester, which remember is always there, and then we throw in whatever alkyl halide we want to start with. So this is our variable. Alright, this is our variable. This is what we choose to start with. Depending on the products you want, you essentially start with an alkyl halide that's 2 carbons shorter. Okay? First step is deprotonation of one of the acidic hydrogens by this ethoxide, and then second step is addition of acid and heat, and this is where we'll go through exactly what happens here because the mechanism is a little bit involved. All right? First thing though, let's just follow some arrows. We know the ethoxide is going to grab the most acidic hydrogen in the molecule, and it puts those carbons, puts those electrons, I should say, onto this molecule. All right. So let's just draw that out. That goes down here, and so what we end up with is this. Now I'm not going to draw all the resonance structures out. In fact, let me do this a slightly different way. There's actually more than one way that you can draw out how these electrons go, and let me draw them out this way. If this bond breaks, we can put electrons up into here, which can then funnel electrons up into here. All right? And this gives us something that we've seen in a previous video. Do you guys remember what the name of this species is? The name of this species is an enolate. This is an extremely important species in this chapter. This is particularly stable because the negative charge on this enolate can go on this oxygen. It can go on this carbon. You should see if you can push arrows to show the resonance structure between here and here. And then you can also push the electrons up onto this oxygen. So 3 different places where that negative charge can go. All right. And then once you've got your enolate, at that point, what comes into play is your alkyl halide. Now you might ask, well, why doesn't the alkyl halide come into play before then? Well, these hydrogens aren't particularly acidic, so they don't do anything. All right. So we're starting off with, what are we starting off with? Let's start off with this guy. We're starting off with this 2-carbon alkyl halide. Get there in a minute. Okay, and now we're going to show some arrows to see what happens when these two react. You can actually choose whichever of the enolate resonance structures you want to start pushing arrows from. Some people like to start pushing arrows from the negative carbon because that's easier to do, but it helps if you can push electrons from here, so then you can really see what's happening. This is an alkylation reaction, so this group is going to end up bound to this carbon, but I want to see if we can see why. The O-, what it's going to do is to do what it always does, unless it can protonate, and we haven't thrown in our H+ yet. It will send its electrons back down to the carbon-oxygen bond, reforming the carbonyl, and then these electrons come out and attack this carbon. Now, I talked in a previous video about how we know exactly which of these 2 carbons the alkyl group goes onto, so I'm not going to spend too much time on that here. But what we end up with is we have our oxygen, we have our carbonyl, and we've reformed our carbonyl. Alright, so essentially it looks like we have our ester back, but this is now our alkylated ester. Alright. This is called an alkylated malonic ester. If this guy was a malonic ester, Then this guy is the same thing, but it's alkylated. This is an alkylated malonic ester. All right? This is what happens in what we see as step 1 here. Step 2 is when we throw in the acid, and then we see what happens. So let's move on to the next slide for that. Okay, I'm going to draw out the malonic ester again. Right, so it looks something. Sorry guys, I think I'm a little off form today. I don't know what's going on. Here is our alkylated malonic ester. All right. I guess I could have drawn some more of these structures out ahead of time, but yeah. Okay. What we're going to do is we're going to see what happens. We're going to throw in some H3O+, and then we're going to heat it up. Now, through a mechanism that's similar to what we've seen before, hydrolysis of esters, you remember what an ester gets hydrolyzed down to? It's an acid and an alcohol. It's essentially the reverse of the Fischer esterification. So we aren't going to go through the mechanism because we spent part of the class on that. What I am going to do though is to draw out the product that we get. The ester groups are gone and they're replaced with OHs, so what we end up with is essentially a dicarboxylic acid. So that diacid would look something like this. Like so. Okay, so that is our diacid. Now this is where things get a little bit different. Okay, diacids, particularly when there are 1,3 to each other, undergo a very particular and special sort of reaction in the presence of acid and heat. And I'm going to try and give you a way of thinking about what it is that actually happens. It's kind of a sort of a cyclic mechanism. All right. So what I'm going to ask you guys to do is to draw this structure out in a slightly different way. All right. I'm going to take my oxygen, have a hydrogen pointing up here. So all I'm doing is redrawing this thing out in what looks to be a slightly different way. All right. And I may actually give you a different way to look at this if this first way is a little unclear. So all I'm doing is drawing out my alkylated malonic ester, but really all I've done is flip this acid group around and have the OH pointing up there. Essentially, what happens is, I'll give you what I would say is the more involved version first. All right. Let me get this right. The electrons on the oxygen, there are 2 electron pairs on this oxygen. The first thing they do is grab that hydrogen. All right. In doing so, that carbon-oxygen bond has to break. That hydrogen-oxygen bond has to break, and goes down to form a carbonyl group there. Unless this bond breaks, this would be a Texas carbon, so this bond does break and puts the electrons over onto this carbon, forming a double bond here. And then to prevent this from being a Texas carbon, these electrons on this pi bond go back up onto the oxygen. Now, that's what we call a cyclic mechanism, and that's relatively involved. Let's see if we can follow that. The important thing is, I'm going to draw out what we have on the left-hand side first. Okay, we have a carbon, and we don't have a carbonyl anymore. We have an OH, and actually we have another OH, the one that didn't do anything, and we have a double bond, and we have this. Now this is a very odd-looking species. This is an enol acid, and it's rather unstable. Enol acid, you have 3 functional groups coming off the same carbon. It's not very stable, and it rearranges to something much more stable. But look at what else we get out. This bond goes from here to here, so you now have 2 double bonds to the carbon, and that bond breaks. So essentially this whole piece splits off from the rest of the molecule, giving you carbon dioxide. All right. This reaction is known as a decarboxylation. All right. D because you're losing the carboxy group, or CO2. All right. So CO2 comes out. All right. Before we get to what this rearranges to, also notice that on the first slide it said we got 2 equivalents of ethanol. Now those are a result of this acidic hydrolysis here. All right. So if you're wondering where those two came from, that's where they came from. This guy, this unstable enol acid, then, and just to indicate that it's unstable, we're just going to put it in brackets. All right. This thing rearranges to give. Let's see if we can figure this out. Well, what it rearranges to give is essentially carboxylic acid. Alright, so it looks something like this. It's a carboxylic acid that has 2 more carbons than the alkyl halide that we began with. 2 carbons here, 4 carbons in the acid. Right. Now, if you were to look at a possible mechanism for this, it's virtually identical to the mechanism that enols undergo tautomerization to ketones in the video that we saw for keto-enol tautomerization. So overall, what this mechanism is the way to take an alkyl halide, add 2 carbons to it, and make a carboxylic acid in the process. Right? Now, let me look at one more thing here. I'm going to draw this out again. I'm going to draw this guy out again and maybe give anybody that didn't really understand what happened the first time maybe a simpler way to follow the electron flow. Personally, I like this one because it shows me exactly where everything is and how it's going and what it's going to, but I'm going to draw another one out and show you essentially what the book shows. The only issue with what the book shows, it doesn't really show you that much. What it shows is the electrons from this bond grabbing that hydrogen, and that ends up on the oxygen. This bond breaks and goes down here, and this goes onto here. So these arrows and these show you the same thing. This gives you a little bit more detail, but that's just my personal preference. All right. So overall, the malonic ester synthesis allows you to go from malonic ester and an alkyl halide with N carbons to a carboxylic acid with N plus 2 carbons. And that's it.